Hey guys, how's it going? So in the last tutorial on BURAI, which is a GUI of Quantum Espresso, I showed you guys how to run a SEF calculation. Now in this tutorial, I'm going to show you guys how to run a band calculation. So basically we will be, calculating the band structure of silicon. So in order to do that, just go ahead and click on bands right here. And by the way, I'm working on the same project that I was working in the last tutorial. So in case you guys skipped it, you might want to watch it, or if you can keep up with me, then you can watch this one also. So coming to this band tab, so here there are not a lot of options that you need to set. So basically you have the number of bands that basically tells the number of bands that you want to be calculating. So for the silicon crystal structure, what I want is I want almost I want to calculate the same number of bands in the valence band as well as the conduction band. So here are a few examples of the silicon band structure on the internet. So we'll be trying to produce a graph that looks somewhat like this. However, there is one thing that you need to keep in mind, that these plots have been produced using a 2-atom silicon crystal. However, we are working with an 8-atom crystal, so there will be more bands in our system. So as you can see here, they had like 4 bands in the valence band and a few more in the conduction band. However, we are working with 32 bands, and the reason is because in our case we have 16 bands in the valence band or the occupied levels. So how do I know that information? That is because if you go ahead and look at the result in the SCF calculation, so basically what you do is you run an SCF calculation with the occupation set as fixed, and you don't provide any information of the bands right here. So when you run this calculation, then what you notice here is you will notice that your Quantum Espresso will calculate the energies at each k point. So as you can see, at this k point it has calculated a few energies. Now all these the number of these energies is 16. That is 1 2 3 4 5 6 7 8 times 2, that is 16, and it has evaluated the highest occupied level 2. So basically it has only worked with the occupied levels, and since there are 16 occupied levels, so I know that I will need to go, or I will have to provide an n band that is larger than 16 to plot the conduction band. So you can either put it as 32, or maybe to run the calculation a little faster, what you can do is you can just set it to 24. So there will be 16 valence bands and there will be 8 conduction bands. And then you have this option of symmetry of bands that you can set to true or false. And then comes the important part, that is the high symmetry points, or the paths that you want your reliance or integrations to be done on. So currently BURAI, what it does is it refers to the geometry of your system. So currently it is set to cubic. So what it does is it automatically picks out the high symmetry points of the cubic lattice, and then it performs the integration along those. However, we know that silicon is not just a cubic lattice, but it is also an FCC lattice. So I mean, it is a diamond FCC lattice. So we should probably if you go ahead and look at all these graphs, then what you can notice is they have evaluated the band structure along the FCC high symmetry points. So cubic has the high symmetry points as gamma XM, gamma RXMR. However, FCC has these as like okay, so there was an image right here. So the high symmetry path for your FCC lattice is gamma XWK, gamma LUW, or something along these lines. So we should be using this. Now coming back to Quantum Espresso, so you want to change these, right? So currently there are 2 options, that is you can either change them through the input file. So we have the good old input file, and you can perform the changes here, or you can perform the changes here. Now the question that we have is how to perform these changes. Now before we go ahead and do that, for the sake of this tutorial, let's just go ahead and run this calculation with these symmetry points only, that is for the cubic lattice, and let's see what is the result that we get. So just go ahead and click on run. Okay, so the calculation has started. Now it might take a lot of time, so what I'm gonna do is I'm going to pause the video now. So I mean, you can see that the band's output file has started to be calculated. So what I'm gonna do is I'm just gonna pause the video right here and resume when this calculation is over. Okay, so the calculation is finally complete, and if you go ahead and open the bands file, then you will see that in the end it says job done, and then the bands up file it also says that the job is done. So basically it means that the file is complete. Now in case you're wondering what these two files really mean or what do they calculate, then basically the first output file is from the pw.x output file. So what it does is it calculates the energies and all that stuff for all the bands, and then this output file is basically from the bands.x. so here you can see that it says that the program's name was bands, while here the program's name is pwscf, because this is the output file from pw.x. So what this file does is it is an kind of a post-processing tool, and it basically just tells you the x coordinates for the high symmetry points. So the gamma point corresponds to the x coordinate 0, then the x point corresponds to the x coordinate 0.5, then m, then gamma again, then xmr or something like that. So basically it just gives you all that information, and then it tells you that the plottable bands have been written to a file called espresso.band1.gnu. Now when you perform this calculation, usually what you do have is that BURAI basically just plots all these bands and gives you a file called bands. Now for some reason I didn't get that when I ran this calculation, and it's probably that because usually it is expected to run the DOS calculation also. So I've noticed that when I run the density of states calculation, then it magically appears, but for some reason it did not evaluated that currently. So let me just go ahead and do that manually. So if you go to your project, wherever you save your project like siscf.test, then you will notice that there will be a file called espresso.band1.gnu. so just go ahead and open it using any text editor, and then just select all these values and plot them in any plotting software. So in my case I'll be using Origin, so just select all these and then plot them. So here you get the band structure when you evaluated it along the cubic high symmetry points, that is gamma, xm, gamma and all that. Now coming back to the silicon band structure, now if you go to these links on the internet, then you will notice that they have evaluated it along the high symmetry points of the FCC lattice, as I already told you guys. Now in case you're wondering how to do that using Quantum Espresso, then the answer is pretty basic. Now just listen to me very carefully. Now you need to understand what all this means. So for SCF calculation, we had k points set to automatic here. So we had automatic keyword here, and then we had a grid like a 8x8x8 Monk pack grid or something like that. But for the band structure, you need to specify the path. So that is why you have the path. Now since the newer Quantum Espresso, it gives you the ability to, instead of writing the complete coordinates of the gamma or the x point, then instead of that what you can do is you can just write these short notations for all these high symmetry points. So for gamma or any Roman numeral, you can basically just write the lowercase version, the letter in the lowercase and then the uppercase. So basically gamma corresponds to G, small g, and then capital G, and then x, m, and then gamma and r, x, m. So for FCC lattice, I already told you that the high symmetry points are like w, gamma, x, w, l. Now the problem here is that currently Quantum Espresso is set to be considering this as a cubic lattice, since I bar is equal to 1, and therefore it will not recognize the w, l, etc. gamma point high symmetry points that correspond to the FCC lattice. So I can just go ahead and show you that real quick. So if you change it to w, which is a high symmetry point for the FCC lattice, then if you just go ahead and click here so that the changes reflect, and now if you run this calculation, then you will probably run into an error. So as you can see that our calculation crashed, and if you go ahead and look at the reason, then you will find that the letter w is not recognized. So what you need to do is you need to provide the explicit points for all these. So the way to do that is I mean, you can just Google those and you can find out the coordinates for all these points for the FCC lattice. So here I have a link where all these points are mentioned in two ways. That is, you have the crystal coordinates as well you have the coordinates in 2 pi by a, that is the reciprocal lattice. So Quantum Espresso provides you the option to enter the coordinates either as in the reciprocal lattice, that is 2 pi by a, or in the crystal coordinates. So you can choose whichever you want. It doesn't make a lot of difference, because as you can see that in the crystal coordinates also you had the x point as 0, half, half, and then in the 2 pi by a, in terms of 2 pi by a, you will have these as like 0, 1, 0. So there's not a lot of difference. And similarly in L you will have like 0.5, 0.5, 0.5, and then you will have half, half, half of 2 pi by a all here all. So that's how you will be providing the coordinates to perform a band structure calculation, so that you get a band structure something like this. So I have already went ahead and noted all these points in a in a notepad file. So we'll be calculating the band structure along these 6 points, so WG. And let me just show you one more thing. So basically K points tells is in input card, then 2 pi by T pip A underscore B basically means 2 pi by A. You can either change it to crystal or automatic, but for band structure calculation you only work with these two. And then you can enter the coordinates either here by double clicking here and entering like 0, then pressing enter, and then if you reload this, and you will see that the changes would have reflected here. And then this basically tells the number of high symmetry points that you are working with. So currently we have like 1, 2, 3, 4, 5, 6, 7, 8 symmetry points, that is why it is 8. And then these points, that is 20, 20, 20, basically what these are is what Quantum Espresso basically does is, when you provide two symmetry points like W and M, then what it does is it performs the Boolean zone integration along this path. So this is basically a line. These 2 points correspond to a line, and then 20, that is the number after W, basically tells that how many points will be on this line that will be calculated. So the higher is the number of points, the better is your calculation. So basically now I have told you pretty much everything that you needed to know, and let's just go ahead and copy this and then paste all these values here, and then just click here so that these changes are reflected here. So now we are going to be calculating the band structure along the high symmetry points of the FCC lattice. So just go ahead and click run, and again I'll just probably pause the video so that it doesn't take up a lot of time. Well, let's just wait and see for this to complete. Okay, so the band structure calculation is finally complete. As you can see here that the job is done, and once again there is some problem, and BURAI hasn't calculated the band structure in a graph. So I'll again have to go and edit this notepad file and reload it, and then just select all these values and go ahead and then plot them in origin. So just create a new worksheet, paste these all there, and just plot them. Okay, so here is the band structure, and now let's compare it with the one on the internet. So comparing it now, just hold on a second. Okay, so now we have this curve coming in pretty good. So we have this line, then this, and all that, and then we have this one also there, so that is also good. Then we have this band also here, so this extends from here to here, and then we have one or two more similar bands here. So basically you can see that the band structures are pretty much same. However, the reason that I have so many bands here is because I had 8 atoms in the crystal, so therefore there were like 16 bands in the occupied levels. So therefore we have 16 here, and then we have like 8 bands here. So in total we have 24 bands, while they only have like 4 in the occupied level because they are using a 2 atom silicon crystal. So They have like 4 bands in the occupied levels and then 4 or 6 more in the conduction band. So you can see that the band structures look pretty much good, and I think they are almost similar. And in case you're wondering like where do these W, gamma, X, W points come in, then you can always have a look here in the band.up file, and you can see that the X, or the what was the next one, the gamma coordinate is at 0.9354 and the first coordinate is 0, so W, so this one is the W. Then we have the gamma coordinate at 0.9354, so somewhere here. So we have the gamma coordinate here, and then we have the X coordinate at 1.6, so 1.6 or somewhere here. So here we have the X coordinate, so comparing it with here, so yes, okay, so this is the X coordinate. Now as you can see, it is all coming in pretty good. That is exactly where it should have been. So I would call it a good graph. And in case you have any doubts or questions, then leave them in the comment section down below and I'll make sure to get back to you. And that's it. I guess I've given you all the information in order to calculate the band structure using BURAI and Quantum Espresso. I hope I didn't miss anything, and I hope that you guys learned something from it and enjoyed this video. In case you did, then don't forget to hit the like button and subscribe to my channel for more videos like this. That's it. Thanks for watching and have a great day. And one more thing, guys, I'm really sorry, but I think I made a mistake. We should have used crystal units here, because I was using crystal units from here. So I made a mistake, and just let it stay at 2 pi by a, but it should have been crystal units. So you can run this calculation once again and see if this makes any difference. Well, sorry.